Alright guys, welcome to this page of the notes, and now what we're going to do is we're going to take a look at the addition and subtraction operations when it comes to nth degree radicals. So we're going to look at addition and subtraction. And in order to add and subtract, just like with the algebra that we've done already, the only way you can add or subtract terms is if they're like terms, meaning the variables and the powers have to be the same. Well, it's a very similar situation here when it comes to nth degree radicals. It turns out that you can only add or subtract if they are like terms or like radicals. Two radical expressions are called like radical expressions if both the indices or the indexes and the radicands, what's under the radical symbol, are alike or the same. So two things have to happen. The indexes have to be the same, and what's under the radical symbol, the radicands, have to be the same. Let's take a look at a couple of examples for you. I have 2, 4th root of a 3a, and 5, 4th root of a 3a. Are these like terms? Yes. Why? The indexes are the same, 4 and 4. The radicands are the same, 3a and 3a. Doesn't matter that the leading coefficients or the constants out front are the same. That doesn't matter. It's the indexes and the radicands must be the same. A couple that are not. Square root of 3, cubed root of 3. Yes, the radicands are the same, 3 and 3. Awesome. The indexes are not. No good. No bueno. The next one. Index is 4, index is 4. Awesome, except radicand 5a, radicand of 5. Not the same, so these are not like terms. You could not add or subtract them. So two things. Indexes must be the same, and the radicands must be the same. Let's take a look at what we're going to ask you to do with these guys then. Here we go. We want you to simplify this guy. I'm asking you to add and subtract some square roots. Well, we go ahead and take a look at it, and here's what I find. Square root, square root, square root. All of the indexes are 2. Fantastic. But the radicands, 12, 27, and 48. Those are not the same. Except there's some stuff that we can do to these. Check this out. I can rewrite this as 2 times the square root of 4 times 3. Yeah, 4 times 3, right? Because 4 is a perfect square and 4 times 3 is 12. Awesome. I can rewrite the next one as the square root. Well, 27 is 9 times 3, and 9 is a perfect square, so we'll do 9 times 3. And I can rewrite the next one as 2 times the square root of 16 times 3. 16 times 3 is a 48, and 16 is a perfect square. Let's go ahead and take care of that. So that means I now have 2. Square root of 4 is 2, and I have the square root of 3 minus 3. Square root of, square root of 9 is a 3, and I still have the square root of 3. Plus 2. Square root of 16 is a 4, and I still have the square root of 3. And do you see what happened here? Look at this. 2, 2, 2, 3, 3, 3. These are now like terms. I'll be able to add and subtract these. Let me go ahead and do a little bit of quick work here. 2 times 2 is going to be 4. Square roots of 3 minus 9 square roots of 3 plus 8 square roots of 3. And so we wind up with a final answer. 4 minus 9 is going to be minus 5 square roots of 3 plus 8, going to be 3 square roots of 3. Oh, that's a terrible 3. All right, so I love the way that these ones work. You're going to start off with something that doesn't look like they're like terms. With a little bit of work, you can get them to be like terms. Go ahead and add and subtract them. Not always, though, right? It won't always work out that they're like terms, so just be careful. Watch out for it. I will definitely give you some where even though you can simplify a little bit, you're still not going to wind up with them all being like terms. That's okay. It'll happen. Let's try another one. Once again, indexes are the same, 2, 2, and 2. That's all good, but 8, 32, and 18, no bueno. Let's go ahead and see if we can fix this. 8 can be broken up into a 4 and a 2. 32 can be broken up into a 16 and a 2. And 18 can be broken up into a 9 and a 2. Well, look at that. Square root of 4 is a 2, so I'm going to have 3 times 2 times the square root of 2. Plus 5, the square root of 16 is a 4, square roots of 2. And the square root of 9 is a 3, square roots of 2. Keep going. 3 times 2 is 6, square roots of 2, plus 20, square roots of 2, minus 12, square roots of 2. Well, let's go ahead and do all that. 6 plus 20, it's going to be 26. Square roots of 2 minus 12 gets you 14 square roots of 2. I got one more for you here, but I think you probably are getting the hang of it. Let's see how this goes. 2, 2, 2. Indexes are all the same. The radicands are not. Gee, I wonder. Well, let's see. 12 I can break up into the square root of a 4 and a 3. Okay. Minus 2. 27 I can break up into a 9 and a 3. 108. Whew. Little tricky. Turns out, yeah, 36. 36 and 3. 36 times 3 is 108, and 36 is a perfect square. Here we go. Square root of 4 is a 2, so I have 5 times 2 square roots of 3. Square root of 9 is going to be a 3, so I have 2 times 3 times the square root of 3. And the square root of 36 is a 6, so I'll have 6 times 6 times the square root of 3. And there we go. Now they're all like terms. That's going to be 10 square roots of 3 minus 6 square roots of 3 plus 36 square roots of 3, and what we wind up with is 10 minus 6 would be 4 square roots of 3. 4 square roots of 3 was 40. How about 40 square roots of 3? Again, I just did 3 example problems where I was able to simplify them all down to something that were like radicals. Please don't think that that will always happen. It won't. There'll probably be a couple in the homework that you're given or possibly on a quiz or a test where you simplify, and maybe a couple of them turn out to be like terms you can put together, but you might have one that just doesn't work out and you'll have to leave it separate. So just be careful. Don't think that they're all going to work out. They won't always. They just happen to here, but they don't always have to. Head on over to the next page of the notes and we'll start taking a look at multiplying and dividing, the operations of multiplying and dividing, and what we can do with nth degree roots when it comes to multiplying and dividing. So I'll see you guys on the next page.